one more example here of two objects connected that will then move with the same magnitude of acceleration. In this case, we have two blocks, the top one labeled m, the bottom one labeled 2m. Our problem tells us that m is 2.2 kilograms. So the mass on the incline, 2.2, the hanging one, essentially 4.4. The problem is asking us to calculate the tension in this connecting string. They give us a coefficient of friction between the mass and the incline, and that's it. So, what we want to do, let's imagine we have these two masses, we've placed them with that string hanging over the pulley. What do you expect to happen? Well, I expect motion. I can't guarantee it will move, but I absolutely cannot assume it will not move. So what we want to do is, if it ends up moving and accelerating, what direction do we expect that acceleration to be in? Well, I would expect the mass on the incline to head down the incline, and then the hanging mass to head down towards the ground. There's nothing, no external force, no other contact force to pull the mass on the incline upwards. And so my only assumption can be that it will go down the incline. So from here, we want to draw out and write out our force equations from our free body diagrams. So the mass on the incline, we know it is experiencing a force of gravity downwards, a force of tension down the incline, a normal force because of the surface, and then because they've given us a coefficient of kinetic friction, that kinetic friction would oppose the motion. We do expect the acceleration to point down the incline. So I'm going to choose a coordinate system where the x-axis points down the incline and the y-axis is perpendicular to the incline. You might remember that I suggested always rotating the coordinate system when the object's on the incline. And again, two reasons for that. It makes it so that the force of gravity is the only one in this case that has both x and y components of force. And it makes it so that this acceleration will be only in the x direction, which just simplifies the algebra for us. So when we do rotate a coordinate system, the angle between the force of gravity and the new y-axis is the incline angle, the 30 degrees. And so we can say that this y component of gravity is mg cosine theta. This x component of gravity ends up being mg sine theta. So when we write out Newton's second law, the net force in the x direction on this block. In this x direction, I have tension pointing down the incline. I have this component of gravity pointing down the incline. And then I have the force of kinetic friction pointing up the incline. So all of these three forces together represent the net force. So that needs to equal the mass of this block times this acceleration A that I say that it is going to have. In the y direction, because of my choice of coordinate system, this block on the incline will not have an acceleration. which means the normal force needs to balance out that y component of gravity, the mg cosine theta. The normal force I know comes into play with the force of friction, because the force of friction is always the coefficient times the normal force. So I'm going to go ahead and plug that in, and we can just see where we're at. So tension plus mg sine theta minus mu mg cosine theta, that all needs to equal ma. We know m and g, we know theta, we know mu, so we know these values. We do not know the tension. That's ultimately what the problem is asking us for. And we do not know the acceleration. So we have two unknowns in this equation, which is fine. We have not looked at the forces versus acceleration for the hanging mass, the 2m. So the hanging mass, that one's a little easier in terms of forces. It just has the tension pulling upwards, and then the force of gravity, I'm just going to write it out as 2mg, since we know this mass is twice that previous one. And again, so knowing this acceleration points downwards, we will need to account for that as we write out the net force in the y direction equaling this mass, 2m, times its acceleration in the y direction. So tension is upwards, force of gravity is downwards. That equals 2m, but again, we need a negative sign in here for the acceleration because we know it will be down. So our equation ends up looking like this. We do know m, we know the mass, we know g, so we now have another equation that has tension and acceleration. So two equations with the same two unknowns. The problem itself wants us to find the tension. There's no problem if we wanted to find the acceleration first. Either way, I need to solve one of these equations for either tension or acceleration and then plug it in the other. If I solve for A, let's see, I get tension minus 2mg over negative 2m. If I take this and put it in for A over here, we're going to end up with tension as our unknown. And then we can solve for the tension, which is what the problem is asking us for. So I'm just plugging this in. This m will cancel with this one, but that still leaves me with a negative 2. So if I multiply both sides by negative 2, it will cancel on the right, leaving me with tension minus 2mg. I need to factor it through on the left. Okay, so my unknown is t. I want to get those together. When I add 2t to both sides, I get 3t on the right. I'm going to add 2mg to this other side. Getting a little sloppy here, sorry. Okay, I'm going to factor out 2mg just for calculation purposes. I don't have to plug it in every time. And divide by 3. This calculation will allow us to solve for the tension. So the mass they gave us was 2.2 kilograms. The angle, I believe, was 30. Let's double check. So 30, yep. Mu was 0.18. So plug these all through. I'm getting 9.427, which I believe we have 2 sig figs. So yeah, 2.2, 0.18. So the tension here is 9.4 kilograms. Oh, I'm wrong on my units. I didn't solve for a mass, I solved for a force. And the units are coming because mass is in kilograms, g is meters per second squared. Kilogram meters per second squared is a Newton. So that is the tension in that string connecting the two masses in this case. You could, if you wanted to, solve for tension first up here and plug it into the other equation and solve for A. Get the acceleration and then take that back to either equation and solve for the tension. That would be perfectly valid as well. In either case, though, we end up needing to draw our free body diagrams, write out all the forces. Second law, net force equals mass times acceleration, in order to fully relate the forces to the motion.